everybody. Welcome to DjangoCon. I am Brandon Rhodes, and my talk this morning is called On the Revolutions. I'm going to be speaking about perhaps Poland's most famous scientist, Mikołaj Kopernik, who lived north of here, went to school south of here in Krakow, and also went to several universities in Italy before returning to Poland and publishing at the end of his life his great theory. He lived right around the year 1500, and his famous work was called On the Revolutions, that is the rotations of the celestial spheres. He became famous for being the person who best argued that in our mental model of the universe, we should lift the Earth into the heavens and have the sun at the center instead. This was very, very disturbing in medieval times because they believed that the heavens were perfect and pristine and unstained by human evil. And to propose that the Earth was not at the bottom of the universe, but that it in fact rode in the third heaven above both Mercury and Venus, well, it meant that evil, wickedness, poverty, the Soviets, everything that has ever happened on this Earth happened in the heavens. It meant that there was perhaps in the universe no barrier to how far evil could travel. It was very disturbing. And what I want us to do today is look at why he made this startling proposal that we're not at the bottom of the universe. The near-Earth environment had been very well mapped to accurate scale by the Greeks just before the turn of the calendar. Aristotle put together arguments from several previous philosophers and made the definitive proof that the Earth is a sphere. Eratosthenes, 100 years later, was then able to measure the Earth's radius by looking at the angle of the sun from two different locations. And by the 100s, Hipparchus had actually gotten a good estimate of the distance to the moon. So what the guys at NASA call the near-Earth environment was already very well mapped before the beginning of the first millennium. The question came up about what lay beyond the moon, where we could yet measure no dimensions. The data is very simple. Every day, sun and stars come up in the east and go down in the west. But if you look at the sky every night, you will see that some of the stars, they were called the wanderers, or in Greek, the planets, they didn't make it all the way up the sky each night with the other stars, but lagged a little bit behind them, and thus, over the years, moved from the west to the east across the sky if you checked every night. And then, instead of having the planets didn't move simply in a single direction, let's see. If you're looking at the sky, then that end will be the east end of the stage. So the planets didn't just simply move east, they would move forward and then back up, and then move forward farther and then back up. And that little period of backing up was called retrograde motion. And in the old model, which was most definitively assembled by an ancient astronomer named Ptolemy, he did what any reasonable systems engineer would do today, taking a Fourier transform, seeing a system that seemed to have two periodic motions in it, a big one that went the whole way around the sky, and then this little back and forward motion superimposed on top of it. He hypothesized that the planets were carried on pairs of spheres, a big one that provided the main motion, and then a little bitty sphere that rode on that one and provided the sine wave or waveform that moved the planet back and forth in its retrograde motion. Copernic had a different idea because he followed a minority opinion among Greek scientists that was supposedly started by a legendary figure named Pythagoras. This is what Copernic said. First, I found in Cicero that Hisatus had realized that the earth moved. Cicero was an ancient Roman author. And later in Plutarch, that others had held the same view. He also knew, though he didn't state it in his book, that a particular Greek, Aristarchus of Samos, had suggested the sun was fixed like the stars, and that it was the earth that was moving. So given that these ideas had been around for maybe 2,000 years by the time Copernic wrote his book, why was nobody taking these ideas seriously? And the answer, interestingly enough, is that medieval and early Renaissance scholars were too empirical. They cared too much about physical evidence that was right in front of their eyes, because it's quite clear, it seemed to them, that I'm not standing on a moving platform. If I were to throw something up in the air, it would come right back to my hand, not, if you release a ball, it doesn't shoot sideways at 700 kilometers an hour because you're on a rotating planet. You're clearly on a stationary one. And then there was a clinching argument that if the Earth was really moving millions of kilometers a year back and forth around the sun, that should slightly change the perspective we have on the stars, but no variation in the position of the stars had ever been measured. It was this lack of physical evidence that was decisive at Galileo's trial 90 years later, when the church got angry with Galileo for saying that Copernic had not had a theory, he had known the truth. The cardinal who ran the trial said in his conclusion, I say that if there were a true demonstration that the sun was in the center of the universe, we, the church, would have to say that we just hadn't understood the scriptures that say it's the sun that moves, then to, say that something was false, which you scientists had demonstrated. But I do not believe that there is any such demonstration. In this whole trial, none has been shown to me. Now, so despite the fact that there was no physical evidence that we were on a moving platform, the scientists kept developing these ideas. Kepler, an astronomer, I believe, in Italy, developed, we'd never quite been able to predict the exact positions of the planets using spheres, in using circles. And Kepler discovered that if you use ellipses instead, you can exactly predict, without any remaining error, the positions of the planets, which was huge. No one had ever exactly predicted the course of a planet before, and it required the sun to be at the focus of the ellipse, not the Earth. Galileo perfected the idea of inertia, which would explain why when you throw a ball up, even if you're on a moving planet, it doesn't shoot sideways. And Newton finally came up with the idea that if the planets were attracted to each other by a simple inverse square law, it would produce exactly the elliptical orbits that Kepler had derived. So everything was theoretically in place and just waiting for physical evidence that the Earth moved, and it didn't appear, finally, until 180 years after Copernic published his book. In 1725, I believe an English scientist named Bradley finally proved that we were moving. And it was it was the biggest surprise in the history of science. As we got better and better and better telescopes, we kept expecting to see stellar parallax. Surely the next telescope will be good enough that we can see some of the stars moving with respect to the other as we go back and forth in our orbit. And the instruments got more and more perfect, and Bradley could see every star in the sky going in a little circle. That took 1 year. All of the stars in the sky going in tiny, tiny circles. Oh, that helps. And he made his name and his fame for all time have you ever been in like an automobile driving into a snowstorm or a rainstorm, and because of your velocity, it looks like the snow is actually coming from a point up in front of you? Another scientist had already begun to claim that light took time to travel and was not instantaneous, and Bradley realized that if this were the case, then the Earth's motion would make everything in the universe appear to be slightly more in front of us than it actually was, and that as the Earth turned a complete, as our velocity in space turned a complete circle through the year, all of the stars would make little circles. And so he was actually able to determine the speed of light by determining our velocity through the solar system by watching all of the stars move in response to our perspective and our relative velocity to the light changing. It was finally in 1838, more than 100 years after Bradley, that our instruments finally became sensitive enough to see stellar parallax. Why did it take 113 years? Because if you want to see stellar aberration, the light from the stars moving because of our motion, you have to get split the circle into 360 degrees, and you won't see any motion. Get your instruments to where it can measure a 60th of a degree, called an arc minute. You still won't see any motion. But once you can measure arc seconds, 60ths of arc minutes, you will see stellar aberration for many stars is about 40 arc seconds. When Bessel measured the stellar parallax to a star 10 light years away, he had to be able to measure fractions of an arc second. So the stars are so far away that we couldn't even measure the distance to them until the last 200 years. It's surprisingly difficult for a species to determine that it's on a moving platform and to prove it. It took 1,900 years after the Greeks learned the distance to the moon for us to find the distance to the nearest stars. And as far as proving that the Earth moved, it was in 1851 that Léon Foucault realized that if you made a two-dimensional pendulum that could move both left and right and backwards and forwards and hang it in a museum, it will precess around, depending on your latitude, each day, and you can have people standing in a museum watching over the hours this pendulum swing as the Earth rotates beneath it. So we did eventually get physical evidence, and it was really Bradley's discovery of stellar aberration that closed the case. All scientists believed in a moving Earth after that. So we did eventually get real evidence that we were moving, but Copernic, Kepler, Galileo, and Newton had to do all of their work in the absence of any real physical evidence. So why did Copernic ignore all the evidence available to his senses and claim that we were in motion? And the answer is because of beauty. Let's express Ptolemies' Earth-centered universe using Python code. Remember, this is a system where Mercury and Venus never go very far from the sun and the sky, so their epicycles were fixed to the, let's call it the arm on which the sun travels through the year. And then there's an epicycle each for Mars, Jupiter, and Saturn that also take one Earth year to go in a circle. And so Ptolemy's model, and I actually looked up the numbers to get them approximately right here. Using Ptolemy's number, this is how you could set up a model of the solar system's motion. Mercury and Venus are on the same kind of course as the sun, but have this little epicycle that carries them to one side of the sun and then to the other, while Mars, Jupiter, and Saturn are on very big, slow-moving deferents, then with a little annual epicycle superimposed on that to provide them with their retrograde motion. Here I'm calculating the x-coordinate. If you changed it to cosines, you'd have the y-coordinate, and you could actually animate this as a little model of the solar system. So Copernic did this. He said, so an ugly asymmetry here is that for the inner planets, it's the annual term, sine of T, which has no coefficient, but then it switches, and for Mars, Jupiter, and Saturn, it's the epicycle that has that suddenly has annual motion. So you see that the question of whether it's the deferent or the epicycle that moves in 1 year flips halfway through the list of planets. And so let's first get each of those last 3 lines, Mars, Jupiter, and Saturn, let's divide each of those lines by the coefficient in front of the annual term, sine of T, and instead put the coefficient, like it is in the first 2 equations, on the component of their motion that is not 1 Earth year in size. Second, let's now just flip those last 2 terms, those last 3 equations to put sine of T in the front. And we're starting to see a good bit of symmetry in these equations, aren't we? We've now factored out the annual circle that every single planet is having to make and lined it up on the left side where Copernic could now say to the planets, you know, it's not you, it's me, and take the sine of T, the annual rotation, out of the equations for the planets and make it our motion instead. So again, going from this picture where every single moving object in the universe has an annual component to its motion, an Earth annual component, and let's just make that a property of our planet instead. So what did Copernic really accomplish? I say he accomplished the most famous code refactoring in all of history. And why did he do it? Not because of physical evidence, there was none. It was because it made the code so pretty. And when I say code, I really mean the reason Ptolemy and all of these other astronomers worked was so they could predict planetary positions. The picture of the deferent and the epicycle wasn't there to satisfy curiosity. It was the algorithm for computing where a planet would be. And he felt, Copernic felt, that the algorithm is just so pretty if you refactor it and make the Earth move. Here is what he says from his book on the revolutions. Ancient, and so in particular, I want to look at what bit of the beauty of this theory first convinced him. He says, ancient philosophers were willing to take the sequence of the planets, what order are they in above our heads, as being in accordance with the size of their revolutions. Saturn the highest, Jupiter under it, and after that Mars. So you order the planets in order with how long it takes them to circle the entire sky. But what reason can be produced by those who put Venus below the sun and Mercury after it? Then it must be, if you make that move, that either the Earth is not the center, or else that nature is random and that there is no system in the order. Consequently, I think we should certainly not despise the argument which was well known to Martianus Capella that Venus and Mercury revolve around the sun. Again, this is the equations we looked at earlier for Ptolemy's model, and the ordering just isn't consistent. If you look at either the period of the sine waves, which is what's after the division sign inside of each sine function, or if you look at the coefficients that are outside, I mean, there's no real ordering here. In particular, the coefficients start by going up, get highest at the sun, which has a coefficient of 1, and then start going back down again. There's no order to Ptolemy's model, but once you've done the refactoring, look at the periods and look at the coefficients. They are now strictly ordered and paired, where you can tell which planets are closest to the sun because they complete their orbits the most quickly. He found that to be such a beautiful pattern that the closer to the sun you are, the more rapidly you should finish your orbit, that he was compelled, against all physical evidence, to declare that this was the true motion of our solar system. It was beauty that drove him to do it. A philosopher of science, Michael Polanyi, I believe he was a Hungarian of early last century, he said, having studied the books of Copernic, what is the true lesson of the Copernican Revolution? The only justification lay in the greater intellectual satisfaction that he derived from the celestial panorama as seen from the sun instead of from the earth. Copernic gave preference to delight in abstract theory at the price of rejecting the evidence of our senses. Or, in other words, it just made the code so pretty. You could call Copernic the great refactorer, and I would like to coin a term. From now on, I'm going to call it a Copernican refactoring, not just any code refactoring you might do, but a refactoring that makes the whole system you're building simpler by moving something new into the center. If I may, I will propose a few modest examples. First, car chargers. Something stunning happened to me a year or two ago. You know, there's USB plugs that let you recharge from the computer, and those cigarette lighter plugs that let you recharge from your automobile. Well, I'm old enough that I remember when cars didn't have USB plugs, so for the moment we'll go with this. And so for several generations of devices that I owned, I wanted to use them in the car and run their batteries dead in the car. So I made sure that I always got the cord that plugged into the car as well as the cord that would plug into my computer. And then one day I was shopping and I saw it. My mind was blown. I couldn't believe it. My reasoning, literally, I don't know what this says about me, but my reasoning had always been, if the cable doesn't fit, I guess I need another cable. It had never occurred to me to fix the receptacle instead, and to me, this is a very simple example of making a problem easier by, instead of making, so to speak, making your cables revolve around whatever kind of receptacle happens to be available, you instead make the receptacle change to fit the one cable that I now buy with each device that I own. I own a very old Mercedes, a 1984 300D, and my wrench couldn't fit to get to the fan bolts because it was kind of a big, fat, less expensive wrench. I went online and I bought a much more expensive wrench that looked thinner to me, and indeed it was, and I got the fan bolts off. I mentioned this on the Mercedes mailing list, and the esteemed Henry Van Cleef was rather appalled that I had gone and bought the most expensive wrench available solely to get off Mercedes fan bolts. He said, when you can't get to a bolt, it's special tool time. That's when you take your bench grinder and to the box wrench and grind it away to reduce your wrench's height. He said, I have several box wrenches ground at various points, heated and bent for dealing with nasty fastener locations. And I was like, oh my gosh, You mean I can just change my tools? Because again, I had always thought you buy a tool and you take care of it and it was given its special shape at the factory. It had never occurred to me that I could just grind them and melt them to make them fit the situation I needed them to. And so I find that there is, with me, and the way my mind works, a kind of general principle well illustrated by this old Far Side cartoon. Here, two settlers are hiding behind the wagons and saying, one of them is saying, "Hey, they're lighting their arrows. Can they do that?" And I often find that I'm in the same situation without even ever having formulated the rule. I behave as though there's a rule I have to obey that isn't actually there. There's no rule that I can't change the receptacle to fit the cord. There's no rule that I can't, what was my previous example? Yeah, there's no rule that I can't grind my wrench until it's thin enough, but it's like there's this barrier there, and I'm acting like there's a rule even when there isn't one. I'd like to now to suggest three of many, many examples I could bring up of the way Copernican refactorings happen in code. All of you have probably experienced dependency injection, where instead of letting your little routine that's going to go check Twitter use URLlib itself, you instead pass it as a parameter the URL open function to use so that in your tests you can pass a fake one. I actually find that really, really, really ugly to both import a bunch of standard library stuff and then have to pass it all. So the other day I came up with, a year ago, I came up with something I called wishbone splitting. I mean, I didn't blog about it, so my name didn't have to be any good. But I found in a lot of my projects, I started taking all I/O out of my lower level code. My code used to have ideas up at the top and I/O down at the bottom, which meant that I couldn't test any of it without monkey patching. So I instead decided to get, going back, I got the first line of this function and the last line of this function. Everything that doesn't do I/O, I pulled out into separate pieces, and then I had the top level of the code do the I/O. And that way, all of the functions were easy to test. Well, it turns out, I discovered late last year, that I was not the first to have this idea, and there are in fact entire architectures. One of the most best diagrammed, and it kind of looked like a solar system, is the clean architecture. You can go read about it in the original blog post that this is taken from or somewhere else. But the idea here is that you do a Copernican inversion and put all of your I/O and things like that on the outside of your application, and all of your actual business logic is in simple functional code that has no side effects. Another inversion that I love is DaCop, that I believe came out last year, written by a man named Vladimir. The old way of doing things was to instantiate an argument parser from the argparse module, and it would print out some help for you. The problem is that I find the help very, very, very ugly. And it's almost impossible to customize. If you want it indented a little differently or want new lines in other places, it's very, very difficult to get it looking like what you want. So Vladimir's idea is, why on earth are we trying to get a computer to write documentation? How about you just write the documentation for your command line and DocOpt parses it and then checks the command line arguments that have been checked in. And again, this was for me one of those mind-blown moments. I'm like, oh my gosh, that's incredible, and I've been using it ever since. It's a very, very powerful way of inverting the way that we'd been working, where you start with the documentation and just let the computer read it too. Finally, I'd like to suggest that Django and web frameworks in general are a last wonderful example of a Copernican refactoring. If you ever wrote old like CGI code where your program just starts up and has to talk HTTP, your actual business logic tended to wind up buried in a bunch of if statements, checking for the various URLs that you supported. Your program itself had to have all of the 404 messages that could possibly be produced. And with Django, the universe flips inside out, and all of a sudden, the main task of your of a web server, which is to 404 the infinity of URLs that don't exist, disappears from your code. All of the logic of URL parsing disappears from your code, and now it's your application logic that gets to live at the center. So, Copernican refactorings are of all refactorings my favorite. The next time you feel like your code and the way you're approaching a problem is making you work at it backwards, stop and think of Copernic and see if you can turn the world upside down. Thank you very much.